Hello everyone. Today I am presenting Iron, a scheme to account for network-based CPU and enforce strong isolation. For longest time, VMs are used for virtualization. Now there's a huge trend towards container for virtualization. Companies like IBM, Google, Microsoft are using containers for virtualization. This is because containers are faster and lightweight as compared to VMs. Because they are faster and lightweight, they have enabled new workloads such as microservices and the paradigm of serverless compute. Unlike VMs, they share the underlying OS and the network stack. Because they share the underlying OS, it is critical for the OS to ensure strong isolation of resources such as memory, network, and CPU. Especially in multi-tenant environments, administrator wants to strongly control the resource allocation and usage for predictable performance. Strong isolation is important for performance, predictability, and efficiency. Here, by isolation, I mean a container should not consume more than its assigned share. For example, if two containers are allocated 50% of the core, they should get at least 50% of the core. Strong isolation in CPU is critical, as containerized cloud run heterogeneous workloads, and the billing is time-based. Thankfully, Linux provides mechanisms such as control groups or C group and network namespaces to ensure isolation. C group ensures CPU isolation by allocating, metering, and enforcing resource allocation in the kernel. For the rest of this talk, I will show how standard techniques used for years to provide isolation by Linux breaks when large amount of network traffic is handled. I will start by showing the isolation provided by Linux is poor and it breaks while handling network traffic, followed by how Iron fixed this isolation problem, and then the evaluation. To quantify the impact of broken isolation, we measure penalty factor. Penalty factor indicates the fraction of time a job takes when it's competing with traffic versus when it's competing with compute. For example, a penalty factor of 2 means that a slowdown of 2 times, which means that a job takes 2 times longer to complete when it's competing with traffic. Consider an example of a heterogeneous workload. We have a map-reduced word count running together with a network-intensive workload, for example, Terasort. Both are sharing the core. Our experiment shows that the word count takes 1.5x longer when it shares the core with Terasort as compared to when it's running alone with the same amount of resources. Broken isolation has practical implications for both user and the cloud provider. If isolation is not strong enough, user can not only experience high variance in the performance, but also get overcharged. For example, if two containers are allocated 50% of the core, orange container may get only 30% because of broken isolation. This results in overcharging. To avoid this interference, cloud providers have to under-provision resources. For example, by allocating a whole core to a container, though the container only requires 50% of the core. The remaining 50% of CPU get wasted. This results in wastage of potential revenue. In this world where the margins are thin, it is really important to efficiently utilize resources. So far, I argued that isolation is important and the fact that isolation is broken. Now I will explain why CPU isolation provided by Linux is broken. Assume that our example where we have word count, a compute-intensive workload running together with a network-intensive workload. The word count is running and a packet comes for the Terasort. As kernel processes network traffic via interrupts, the NIC sends an interrupt. As a result of that, the scheduler swaps out word count and starts processing the interrupt. Though the packet belongs to Terasort, it will get charged the word count will get charged for processing the packet. The word count will get charged for time t instead of t minus delta t. Here, by charging, I mean reduction in the runtime of a container. This implies that word count will get less runtime in future. Time spent in servicing interrupt is incorrectly charged. To ensure strong isolation, OS has to account for this time. In one of the Linux patches, Thomas Glexner, a Linux developer, has described software interrupt as a conglomerate of mostly unrelated jobs, which runs in the context of a randomly chosen victim without the ability to put any control on them. Let's see how Linux got here. Interrupt servicing and management is complex. It was thought there were many trade-offs between isolation, efficiency, responsiveness, throughput, and complexity. In the past, interrupt design focused on efficiency, performance, and simplicity, at the cost of ignoring isolation. However, given new container-based architecture, we need to revisit this belief, centered around these trade-offs. In this work, we show that some of these previously held trade-off beliefs doesn't exist. And isolation can be provided without compromising efficiency, performance, and simplicity. Let us take a deeper look into the network stack and see how a packet traverses the stack. Our stack consists of TCP/IP stack, followed by a vSwitch for virtual networking, and a NSDI driver. When a process generates a packet, it traverses the network stack. Though this traversal is in the kernel, but it is done in the context of the process. So everything gets charged, everything works perfectly fine. However, there are cases where isolation breaks, especially when there is queuing. For example, we are doing traffic shaping. In this example, we are using queue disk for rate limiting. Or it can be because the NIC is busy. In such cases, when a process generates a packet, it traverses the stack, gets in-queued, and after that, the system call exits. Now, it's the responsibility of software interrupt to dequeue the packet and deliver it to the NIC. Sorry. This is done in non-process context, and process may not get charged for this. Kernel tries to service soft IRQs immediately after hard IRQs to ensure low latency. However, this can be done in the context of the currently scheduled process. The current scheduled process may not be the process which is generating or receiving network traffic. When the interrupt rate is high, the kernel tries to minimize soft IRQ handling in process context. It uses a kernel thread called ksoft-IRQD to process soft IRQ. The time spent in processing traffic by ksoft-IRQD is not charged to any process, but it still breaks isolation because it limits the available resources for the containers. For example, if ksoft-IRQD consumes 20% of the resources, now the containers have only 80% to consume. In summary, either soft IRQ processing is not charged properly or is not charged at all. Both breaks isolation. To evaluate the impact of interference, we ran n containers on each core. Each container gets an equal share of the core. One container on each core donates a victim. It runs a compute-intensive workload, sysbench. We measured the completion time of sysbench under two scenarios. When all the other containers are running sysbench, and when all the other containers are running an interferer, which can be a sender or receiver. The penalty factor indicates the fraction of time a victim workload takes when competing with network traffic versus when competing with sysbench. Figure shows the impact of TCP standard at 5 gig. The y-axis shows the penalty factor. The higher is worse. The TCP standard performance varies with the number of flows. This is because of two reasons. One, with the increase in number of flows, the number of acts increases. The second, it requires more protocol processing, both of which are done in soft IRQ. We observe a maximum penalty factor of 1.85. Please look at our paper for impact of UDP traffic. This problem also exists on the receiver side, and it's even worse. The journey of a packet from the ring buffer to the socket is all in non-process context, and it doesn't get charged to the process. We observe similar trends for TCP receiver. The penalty factor increases to 6x as we increase the number of containers. More containers cause more network traffic. So far, I have shown you that isolation is broken in case where there is a compute-intensive workload running together with a network-intensive workload. This is not just limited to this particular case. It also breaks when there is a workload with low network traffic competing with a workload with high network traffic, or even with a workload with network kernel bypass. So far, I quantify the impact of interference. Now I will go over the scheme called iron, which we developed to account for the time spent in network stack on behalf of a container and ensure strong isolation. I will start with the accounting aspect of iron. Before explaining the accounting aspect, let me show you a call stack of a Linux network stack. When an interrupt comes, it calls do soft IRQ. Later it calls do IRQ. Later it calls do soft IRQ, and then rest of the stack. TCP ACK generation and processing is also done down this stack. To account for the per packet processing time, we leverage the fact that this call stack is nested, and the processing of one packet cannot start unless the processing of previous packet is finished. The highlighted functions of the call stack is called for every packet. For simplicity, I reduce the call stack to few functions. To account for the per packet processing cost, accounting per packet processing cost is not trivial because capturing time difference between two consecutive packets is not enough. Because the kernel is preemptible and the function in the call stack can be interrupted at any point. To capture the time spent in processing a packet, iron relies on scheduler data. Schedulers keep track of a cumulative runtime along with the last swap in time. These two, coupled with the local clock, are used to compute the end and start time of a packet. Besides per packet cost, there is also cost associated with the set of functions which are called for a batch of packets. We call it batch cost. We compute the batch cost and divide it proportionally to the number of packets. To compute batch cost, we considered all 6 interrupts, which include high, TX, RX, timer, SCSI, and Caslet, and compute the overhead proportional to the cost of each individual interrupt. On the transmitter side, Linux often batch packets together to minimize the overhead of locking. It is hard to compute the cost of per packet, so we compute the cost of a batch, and we charge each packet within the batch an equal share. There's another issue on the transmitter side. We need to associate a packet with the container at the time of dequeue. To do that, we encode the information of a container while enqueuing a packet, and later they use that information to charge the appropriate container. So far, I have shown you how we account the packet cost. Now I will show you how we integrate this with the Linux scheduler. Our goal is to return the accounted time to a container, which was incorrectly charged. In our example, it was word count. And charge the accounted time to a container which was responsible for the network traffic. In our example, it was Terasort. Linux scheduler keeps global state. This state includes a quota, which is the maximum runtime a container gets in a period. When a task or container runs, it consumes the runtime. When runtime reaches 0, the scheduler moves the container to a throttle queue. At the end of the period, the runtime gets refilled by quota. Runtime, quota, and period are configured by administrator. To run multi-threaded process, Linux also keeps a core local runtime. A task on a core borrows the runtime from the global scheduler. We added a couple of new state variables. One, in global state, we added gain. The gain tracks the time the container should get back because it was charged incorrectly for processing somebody's traffic. And for local accounting, we added additional CPU usage. The negative value indicates that the container was not charged. Positive value indicates the container was charged incorrectly. Whenever a scheduler takes a lock to refill the local runtime, we transfer the additional CPU to the gain. And we piggyback existing locks. We don't take any additional locks. And later this runtime is transferred to, this gain is transferred to the runtime. The scheduler-based enforcement improves isolation. A container is throttled when the runtime reaches 0 and it cannot generate any more traffic. We don't need to drop any packets on the sender side. However, on the receiver side, Even if a container is throttled, the packet can still arrive. Dropping those packets in the kernel is expensive. We need an efficient mechanism to drop these packets. Now I will briefly go over the hardware-based dropping mechanism of iron. Our hardware-based dropping mechanism works like this. We assign a queue to each container. When a container is throttled, we strip the queue from the polling list. From the kernel's point of view, there is no more interrupts, so no more packets. From NIC's point of view, the kernel is busy and is not polling packets from the queue, so it stays in the polling mode. If a new packet arrives, the ring buffer is full, it gets dropped. We evaluated the effectiveness of iron with both control and realistic workloads. I will start by showing the results with the control workload. To evaluate the effectiveness, we ran sysbench with other sysbench and with network interferers. The penalty factor indicates the fraction of time the victim workload takes when competing with the network traffic versus when competing with compute. For evaluation, we flooded the network traffic at different rates. The y-axis shows the traffic rate, and x-axis shows the traffic rate, and y-axis shows the penalty factor. With iron, the penalty factor never exceeds 1.04. It's a significant decrease from 1.85. We observed similar results for UDP standard, where the penalty factor never exceeds 1.04. For receiver, we vary the number of flows, containers, and the rate. And the penalty factor never exceeds 1.05. It's a significant decrease from 6 for TCP and 4.45 for UDP traffic. In some cases, the penalty factor goes below 1. This is because we overestimate the overhead of hardware interrupts. We are currently working on measuring this overhead more accurately. Now I will show you the effectiveness of iron with realistic workload. We ran experiment on a cluster of 48 containers spread over 6 machines. Each job gets 24 containers. We ran, for victim, we ran compute-intensive map-reduced jobs like word count, pi, and grab. For our interferer, we use a trace-based interference, which represents the shuffle phase of terasort. Our penalty factor with iron never exceeds 1.04. Without iron, it goes as high as 1.5. In summary, we evaluated the interference caused by network-based containers, provided harder isolation for network-based processing in containerized environments, ensure accurate accounting of time spent in processing network traffic in soft IRQs, integrated this with Linux scheduler with minimal changes, and proposed a novel dropping mechanism. Thank you.
Are there any questions for Junaid? Yeah.
So regarding the sources of broken isolation, and the reason why some is how the received packets are handled, and the other is how the transmitting packets are handled. So I think they are largely independent, and I mean, according to what you say, I think the more problematic part is receiver side, by which thread receiving packets are processed. Okay, but this is, I think, Linux specific, because in Linux, some of the interrupt processing is done by currently running thread, and this is exactly the reason why the isolation is broken. But in FreeBSD, for example, it runs a dedicated interrupt thread, so in that case, I wonder if the problem exists or not.
So in those cases where you can run multiple threads in the kernel to process traffic for each user space thread. But there the problem is that you need to schedule those threads efficiently. Otherwise, your TCP performance will degrade, because these threads, even on the receiver side, you have to generate ACKs. So your thread should get scheduled to generate ACKs responsively.
Okay, so you mean if the CPU core is busy? For the schedule between some the application thread and some interrupt thread. Okay.
Yeah. So that's one of the reasons why Linux share the per core has this per core thread model.
Any other questions? So I had a question. So you mentioned you added some information to the SKB to be able to do the synth-side isolation stuff. I know that's a big no-no for performance. Like when if you tell people in the Linux kernel, let's add some bytes to the SKB, they will basically jump on you and kill you. So because they will tell you, cache line alignment and so forth. So it's that breaks a lot of stuff. So did you measure the performance penalty, and how many bytes did you actually add to the SKB?
So we just add a pointer to the container task structure.
So that's 8 bytes, right?
Yeah. And we didn't just specifically measure the overhead of that particular part, but in general, our overhead is not that high. It stays like, in CPU terms, it's like less than 0.5%.
So did you measure any sort of network heavy, like UDP-based, send at max type of workloads?
Yeah, we measured this with maximum traffic we're sending. So it's not that high. There are other solutions for that. You can use the IP address to associate a packet with a container. That's the alternate approach if you don't want to modify the SKB.
And one last question: does this apply to VMs? Like, because you mentioned that people are using containers, but of course we all heard about meltdown and all these problems, and all of a sudden the kernel page tables are not in user space anymore, so performance for containers probably dropped a lot. So all of a sudden VMs start to look appealing. So would this be a problem for like VM-based
So this
systems?
particular problem doesn't exist there because they run their own network stack. Here the problem is because you are sharing the network stack and the packets are processed by through soft IIQs, which is shared. So there's work on VMs in the past to ensure isolation. So I don't think this exact problem exists there, but similar problems are there.
Okay. Let's thank Junaid.